amount of chemicals in a solution. So what's the point of this? This is basically to quantify how much of a solution is made up of a specific chemical. So basically a solution is composed of two different components. We have a solute, which is usually a chemical. It could be solutes too, like multiple chemicals. Let's say hypothetically you're making salt water. So salt water, the solute will be NaCl. It's the chemical you're adding. And you also have the solvent. Solvent is whatever you're mixing the solute into. Salt is whatever you have less of. Solvent is whatever you have more of. Your most common solvent would be water, which is H2O. Now, these two together give you what's called the solution. So when we say solution, what we're talking about is a solute and the solvent. And once again, this can be plural. You could have more than one solute theoretically. And the solvent is usually just going to be one substance, and the most common solvent is going to be water, though you can have other types of solvents. All right, so the first calculation we're going to go over is mass percent. What this basically does, it shows you how much of a chemical you have in terms of grams of sample versus total solution. So you can see in this example, you have the solute, which is the salt, or excuse me, the potassium chloride. You can tell it's a solute because it's the chemical you're using. And then what you're going to do, and this is 8 grams of it, you're going to add water to it until you get to 50 grams. The water is your solvent. So solute, chemical, solvent is going to be the water. So the calculation involves the grams of solute divided by the grams of solid plus the grams of solvent, which is also known as your grams of solution. So this is basically grams of solution, which is the two of them together. So in this situation, we have 8 grams and 50 grams is your number. So you plug 8 on top, you plug in 50 in the bottom, times 100, because we're talking about percent. That's the only reason using 100 at all is because with percents, you always have to do that. So let's take a look at the number crunching for this. So you have 8 grams of KCl. You added 42 grams. For those that didn't notice how I came up with that, you had 8 grams to start with. You ended up with 50 total. So the grams of water would have to be 50 minus 8, or 42. You don't really need to figure out the 42 part. I'm just showing you where the numbers are coming from. And the reason for that is that sometimes you're just given these two, and you're supposed to do mass percent with it. So you're supposed to be able to know, okay, it's 8 divided by 50 instead of 8 divided by 42, which is the common brain fart for this. A lot of students will divide by 42 grams, which is your solvent, instead of your total solution. But remember, the division, or what you're dividing by, is always going to be the total mass. That means all the chemicals together. So keep note of that. So when we do the number crunching, 16% of it is going to be KCl. So not a large percentage, right? So what makes a majority of the solution? You don't even need to do the number crunch to probably figure this out. It's water. But let's say numerically we want to figure out what the mass percent of water is hypothetically. Well, if we know that the total percentages have to equal 100, always, by the way, and we subtract the 16 that we got for the KCl, that means 84% of this is going to be water. So that's how you do the number crunching. Now, why would you need to do this at all? Rare situation, they ask you for a mass percent of solvent. Not very common, so I won't worry about it, but just be aware, you could theoretically do that. All right, solution is prepared by mixing 15 grams of sodium carbonate and 235 grams of H2O. Calculate the mass percent of the solution. So what are we going to do? Well, we know that our mass of solid is definitely 15. And for those who are like, well, how would you know it's that? What if you have this random chemical here? The thing you want to look for, whatever you have the smallest mass of, is always your solute. Whatever you have less mass, that's always your solute. Whatever you have more of is always your solvent. So common brain fart for this would be 15 divided by 235, because that's what people do. Don't do that. Remember, it's going to be mass of solute divided by your total mass. You have to add 235 plus 15 to get your total. So let's take a look at this. There's 15. There's your total. So 15 divided by 250. You're good to go. 6% is sodium carbonate, which means that 94% of this is water. So as long as you avoid the brain fart of just dividing by the mass of solvent and making sure you add to get your total mass, sometimes they'll just give you total mass to begin with. You don't have to do the addition. But if they don't, just remember the total mass. All right, parts per million. This is another type of calculation typically used when you have very small amounts of chemicals inside the water, like, for example, contaminants. If you want to know how much lead is in your water, you can probably use parts per million or even parts per billion. Why? Because the number is so small, it's in a decimal form, that we use this to get it out of the decimal form. And what does that mean? Well, let's take a look. So exact same thing as mass percent. The only difference is instead of multiplying by 100, you're multiplying by a million. And why are you doing this? Because your number is going to be looking like something like this. So rather than say you have 0.00001, you multiply it times 10 to the 6th, and you get like 1 ppm. That's the whole point of this, is to avoid the ridiculous zeros before a decimal, or excuse me, after a decimal to give you a very small number. You're going to get something more manageable. Taking a look at this, we have what's the concentration of ppm when 1 times 10 to the -6? So you can see it's a very small mass already. We can see our total mass is 100 grams. Very small number. So what do? We divide, and for ppm, instead of multiplying by 100, like we do for mass percent, we multiply by a million, so you end up with 0.01 ppm. Still a decimal, but better than 0.000001. That's the whole point of ppm. When do you use this? Very small chemicals, but it'll be spelled out for you. It'll be asking for parts per million. It's not going to make you guess which number to use or which number crunching to do. All right, the most common type out of all these is molarity. Molarity is concentration, so they're synonymous. When someone asks you for the concentration of a chemical, they're asking for the molarity. And just to be aware, molarity should be represented with this kind of thing. So this is like 12 molar. They usually put the number in brackets to signify molarity. So if you ever see numbers inside of brackets, that's the molarity, that's the concentration, and we'll see what that looks like in a second. But be aware of the brackets. That's your sign that this is a molarity value. And there is a symbol for molarity, which is big M. So it's concentration of solution. There's your formula, moles of solid per liter solution. Now, all of you guys know liters of solution. You've talked about volume since the beginning of the semester. But a lot of you guys are like, what the heck is a mole? No, it's not a little furry creature that lives underneath the ground. A little bit more complicated than that. It's based on the periodic table. And specifically, what it's based on is the numbers that come from the periodic table. So what is a mole, you ask? Well, the mole is basically a unit used to quantify a chemical. So here's the good news, I guess. All the numbers you see in the periodic table are basically equal to 1 mole. So 1 mole of lithium is 6.941 grams. 1 mole of beryllium is 9.012 grams. And for those who are like, well, I thought that was the mass of a single atom. You're absolutely right. It is. Just as a snafu, you actually get this as also the mass of a mole of a sample. The only difference is atoms is represented by AMUs, whereas this is represented by grams. So looking at can be measured with a tool. And the reason we can't measure this with a tool is because there is no scale for it, but what we can do is do it indirectly. So hypothetically, what we can do is take the mass of a sample, and using the periodic table, we can figure out the moles. Now, if you have exactly 18.998 grams of fluorine, you have exactly 1 mole. But what if you have 9 grams of fluorine instead of 18.998? And let's make this simpler for ourselves and say, you know what, this is 19 grams. Then you could kind of hypothesize already that half of this will be equal to, like, let's say if you have 9 grams, right, instead of 19 grams, what you would need to do at this point is convert that into moles. How do you do that? You divide by 19 grams, which is 1 mole. And then you would get the moles of the sample, which is about half a mole. You can do this for any chemical. And remember, this is our old friend, the T-chart. It's been a while, but I told you guys a long time ago, we use a T-chart for a reason. This is the reason. We'll just do one more number crunch just so you can see it. Let's look at carbon real quick. Okay, 12 grams. What if you have 6 grams of carbon? So we put our T-chart. Now remember the way the T-chart works, the number, the mass, which is the grams, goes wherever it can cancel out. So since we're going from grams to moles, we put the 12 grams on the bottom. Why? Because the G's need to go away. So if hypothetically you put 1 mole on the bottom instead of 1 mole on top like you're supposed to, you should be able to catch yourself because G does not cancel out moles. Anyway, so 1 mole goes on top. So 1 mole will be on top whenever you're going from grams to moles every single time. So 6 divided by 12 gives you 0.001. 0.5 moles. So that's how you do the calculation to go from grams to moles. So let's take a look at this in more detail. The mass in the periodic table is equal to 1 mole, like I just said. This is called your molar mass, by the way. So if I ask you for molar mass, I'm basically asking you to look in the periodic table and get the number from the periodic table, which is those numbers you just saw a second ago, which is underneath the symbol, your mass, more or less. So going from mass to moles requires a T-chart, and there's your calculation again for moles. You have the 6 grams divided by 12, and you get to 0.5. Now, for our purposes, because I don't want you to get caught up with decimals, you could just do this. Just round it to the nearest whole number and go with that. As long as you're in a ballpark, you'll be fine as far as tests and exams are concerned, so you don't have to be exact. So feel free to round. The only number you don't round around is chlorine, which is 35.45. My suggestion for you is make that 35.5. Just because this technically doesn't round up, but if you round it up, you tend to get a little larger number than you should. So this is a way of avoiding that. All right, so how do you figure out the molar mass of compounds? Just add the mass of the elements. So what does that mean in English? Well, this is what it means. For example, what is the molar mass of H2O? You can see there's 2 H's and 1 O. Well, we know O molar mass is 16 grams, right? Remember, it's round to the nearest whole number. H is going to be 1. Why? Because, once again, we can ignore the decimals. So you could just do it in your head. 16 plus 2 is 18. Just do some more. Calcium carbonate. All right, calcium is right here. 40. So it's going to be 40 plus carbon, which is right here. 12 plus oxygen, which is right here. You have 3 of them. So 3 times 16, which is going to be 48. So then you add all these together. You get 40, 48, 50, 60, 100 grams per mole. So when I ask you for molar mass, please make sure you note this, the grams per mole. You need to include that as your molar mass. So here's the number crunching again, so you can see it. 100 grams per mole. Please don't forget the units. If you put grams, you're saying that I have that much chemical. If you say grams per mole, you're saying, hey, I got this from the periodic table. Big difference. A little tougher, you have ammonium phosphate. So a couple different ways of handling this. You could take 14, which is nitrogen's molar mass right here. Add that to, and then you take 4, make that 28, 18. And then 18 times 3 gives you the value. Or you could do it individually and distribute the 3 to each one of these. The problem with these is the parentheses means you're distributing the number inside by this. So it's basically 3 N's and 12 H's instead of 1 N and 4 H's. So you could do it this way, where you just add it together and then multiply this whole thing times 3. Or just do it individually, 3 times N, 3 times 4, which is 12, which is what I did down here. Either way is fine, and it's not a big deal. Plus 31 for the phosphorus, and then 4 times 16, which is 64 for the oxygen, so you get 149 grams per mole. That's how you would get your value. All right, calcium chloride, same thing. Calcium is down here, you can see, which is going to be 40. Chlorine is over here, which is 35.5. So you get 40 plus 72. So you can see here I actually rounded to 36. 36 times 2 gives you the 72. But if you did this as 71, that would have been even a better choice, but I'm not going to ding you either way. It's just more common to do this than this, but it's not a big deal. Anyway, so 4 plus 72, 40 plus 72 gives you 112 grams per mole. Iron sulfate, here's that headache again, so you could do 32 plus 64, which will give you 96 times 3. Get your value there for this. Or 3 sulfurs, 12 oxygens. Really, it's a style preference. Whatever route you want to go is fine. 2 irons, there's the 3 sulfurs, and there's the 12 oxygens. So either way is fine. Whatever you're more comfortable with. All right, solution is prepared by dissolving 25 grams of magnesium chloride in enough water to make 450 milliliters of solution. So here's my grams. I'm going to need this to get my moles, right? We have to do a T-chart for this. There's my volume of solution. It's in milliliters. So hopefully you remember how to go from milliliters to liters. Really simple. Just move the decimal point 3 times to the left, 0.450 liters. So anytime you're going from ml to L, 3 times to the left, fastest way of doing it, get your value. So there's my mole part. I kept the decimals because I got to be accurate on my end, but if you did this as 95, perfectly fine. You don't have to have the exact number. You'll have a margin of error, so don't even worry about it. So anyways, T-chart basically, so 25 divided by 95, which gives you 0.263. So remember the way the T-chart works, this times the top number, which is just same number obviously, divided by the bottom. So put this number first in your calculator, divide, and then put this next to get this. Please don't divide the big number by the small number. That's a common brain fart as well. So here you go. All right, to change the volume to liters, just going to move decimal point 3 times to the left, which we did earlier, and then there's your answer, this. So there's your concentration, and once again, this can be represented as this 2,584. So if you see a number in brackets, sometimes they include the M, sometimes they won't. Not a big deal either way. All right, common use of molarity. Usually used to make specific concentration of chemicals for experiments. Like for example, if I'm making a solution of 2 molar HCl or 3 molar HCl, I use this type of calculation to develop it for you. So here we're preparing a 1 molar solution of NaCl. So the way this works, we can use a volumetric flask. The way a volumetric flask works, the line inside, and you'll be using this later in this unit, represents the total volume. This particular volumetric flask is 1 liter. So that tells you the line is 1 liter. So these are really cool to use because there's not a need to use a graduate cylinder in place or on top of this. Well, all you do is you measure out the proper moles of chemical, which for 1 mole of NaCl or 1 molar means I need to have 1 mole, and 1 mole is 58.5. And for those that understand how to get that number, that's basically 23 plus 35.5, right? So it's just you take the total mass of this, which is 58.5, and that will equal to 1 mole. So anyways, you put that many grams inside. Then what we do, we start adding water. Now you want to fill it halfway with water, dissolve it, and then fill it up to the line. Now, why don't you just fill it to the line to begin with? Here's why. If you do that, solid takes up space, but this hasn't all dissolved. Once this all dissolves, the volume that was originally here, because you added water to it, it's going to be end up somewhere around there. Because that extra mass that's dissolving will take up more space, and then the volume will be higher, so you'll screw up. So whenever you're trying to make a solution inside a volumetric flask, half fill it with water, dissolve the whole thing, then fill it to your line, so you avoid that kind of issue. All right, so steps involved, once again, you take your sample, put it in, add water halfway, then once it dissolves, fill it to the line. So what's the molarity of a solution of 225 milliliters contains 38.5 grams of KNO3? So here, trying to get cute with the wording, they're putting the volume first, or I'm putting the volume first, and I'm giving you the mass second. Really doesn't matter. So move decimal point 3 times to the left again. There's your volume, and this is going to be 0.225 liters. Change this to moles. So let's go to moles first. 34.8 divided by 101.11. Once again, if you divide by 101, not a big deal, perfectly fine. So you get about 0.344 moles, depending on how you rounded your numbers. That's how many moles of KNO3 you have. We write our formula. Always write the formula first, right? So that we don't have brain farts. Moles over liters. There's my moles. There's my liters. There's my value. I am done. That's your concentration. All right, dilution. What is it? Watering something down. You've all experienced this by leaving a soda out that has ice inside of it out too long at the end, or after the ice melts, your soda tastes really bad because, one, all the carbonation is gone over time, but also because now you have more water than syrup, and that's not going to make it pleasant. So common for strong acids and bases. So whenever I make your solutions, I usually have a very concentrated version of it, and I use dilution to get it to a number where it works. Similar philosophy as far as using a volumetric flask. You're just going to add the amount of chemical, but here it's not in a solid anymore. It's going to be in a liquid form because it's already in the solution. And we're going to keep on adding water to water it down to decrease. And you can see the color intensity is different here versus here, significantly different. And you can see by the picture, a lot more solid or Same amount of solid basically, but the amount of space between them is going to increase, and the reason for it is because you have more water, so there's more area for it to move around. You can tell by color usually how concentrated something is. If this is your most concentrated version, you can kind of see what's happening, right? So this is going to be your most dilute solution, because what's happening here is that this has more water compared to chemical, or this has more chemical in comparison to these other four. So as you increase the amount of solute in a solvent, the color, if it's a colored solution anyways, will get darker. So the darker it is, the more concentrated it is. Your best friend for these calculations is M1V1 equals M2V2. You'll be using that pretty frequently, so be aware of it. So the way this works, they'll give you the concentration at the beginning. Okay, we have this, and we have this, and hey, we want to make something of this quantity of volume. Now they could either give you the volume they're looking for, the V2, or they could look for V2, M2. Theoretically, you could ask for any of these. I'm going to try to avoid that as much as possible. So usually you're going to be looking for M2 and V2, just as a heads up. So anyways, you're looking for molarity, so you need to rearrange this equation, right? Really easy. Whenever you try and solve for one of these letters, take the other letter on the same side and divide it out. So if I'm looking for molarity, theoretically at M2, then you would be dividing by V2. All I did is took the V2 underneath. So if I'm looking for V2, your M2 would be underneath. So try not to let the math get to you. Just simply divide out the letter that you don't need on that side. Just isolate it. And you can see that's what's happening here. I'm looking for my M2. So what do? I divide by my V2. Your formulas are either going to be M1V1 over V2 or M1V1 over M2. Those are typically your options for these. So heads up. So now I'm just going to plug in the numbers. 0.6, 0.1, 0.50. So here is my concentration. So this means that this concentration got diluted, right? And it makes sense because we started with 0.18 liters of solution. Now we have 0.50. So that means we add a lot more water to it, right? So you expect the concentration to go down as a result of it. So here's another example. You mix 3 liters of 3 molar of Na2H with 3 liters of NaCl. Concentration of both chemicals changes since the volume of the solution goes from 3 liters for each to 6 liters. What does that mean? Well, you're adding these two together, right? You have 2 different beakers of these chemicals, right? There's 3 liters of this. There's 3 liters of this. This is at 3 molar. This is at 3 molar. And now what we're going to do, we're going to put it into a bigger beaker, and now we have 6 liters. So your overall volume has changed, right? You still have the same amount of solute in each one of them, but the total volume dividing by is changing. So that does mean you're creating dilution. So in this situation, we have 3 liters times 3 molar, and we're adding 3 liters of NaCl. So if we add 3 liters of NaCl, that means that we are basically diluting this. So we're adding more water. Now, that basically, this kind of question, the only point of it is to make you think of what happens when you're trying to add water in a cute way, which in this case, we're adding salt. And you're like, well, wait, we started with NaOH. Why are we adding salt? Yeah, just trying to get cute. That's all this is. So basically, it's going to be the same as it's them telling you, hey, you're adding 3 liters of water to this, which would make a lot more sense, but yeah. You'll see some very interesting variations of this. So what you're supposed to basically do is understand that when you're adding a volume of solution to the original, your total volume does change. That's how you get the 6 liters. So 3 times 3 divided by 6 gives you 1.5 molar of NaOH. And for NaCl, you get 1.5 molar of NaCl. Why? Same thing. You have your 3 molar of the chemical, 3 liters of solution. So that's where you get the 6 liters again. It's 1.5 molar. So by mixing these two solutions, we've basically changed the concentration. So you could take 2 random solutions that don't really react with each other, put them together, and as a result, you're decreasing the concentration of both because of the fact that the new volume overall is changing. All right, so let's take a look at an example of this. What is the concentration of KOH when you have 15 milliliters of 2 molar KOH mixed with 4 or 5 milliliters of KCl? So very similar to the other example. Our total volume is changing. So it's going from 15 originally, which is where it was 2 molar, and we're making a total of 60, 70 milliliters. So as a result, you could already tell the concentration is going to go down. So if you had to guess, you know it's not going to be this number, right? All right, let's take a look at the calculation. There's our setup again. We're looking for M2, M1, 2, 15 milliliters, and there's your total volume again, 60. So yeah, concentration went down. And that's all because you're adding a random chemical that's going to dilute your solution. All right, that's it for how to do concentration of solutions and the different variations of figuring out numerically how much chemical you have in a solution.